All right, so for our second lesson of inequalities, we're going to go into linear inequalities in two variables. So this will be our 9.1. Now, we start the lesson off by asking ourselves to consider the inequality x plus y is less than 12. And they say write a solution to this inequality. When they say solution, it's basically just a way of saying, hey, if I want to figure out what any sort of solution is, it's an ordered x and y pair that satisfies the equation or satisfies the inequality, because we're talking about inequalities, not necessarily equations themselves. Now, let's just come up with some pairings and we'll write up maybe two solutions that work for this. We need an x and y such that when we add them together, they are less than or equal to 12. So let's start off with dealing with like maybe something like 4 for x and 7 for y. Well, if we put these things together, 4 plus 7, and I'm going to write a little smaller just so I can fit it, 4 plus 7 is less than or equal to 12. This is 11 is less than or equal to 12. Yeah, of course, this works. Perfect. So there's one solution. Let's come up with another one. Maybe I put together a negative integer like negative 5, and maybe I put together positive 6. All right, well, if I write this as a negative 5 plus the 6 value is less than or equal to 12, negative 5 plus 6, this is 1, which is less than or equal to 12. Yeah, that also works. So there is another solution. Now, what you're going to notice is that if we're talking about like all possible values that we could potentially put on this to satisfy a specific x and y that satisfies this inequality, there's actually an infinite amount of solutions for this situation. So an inequality in two variables doesn't just have one solution, such as when we talked about our systems of equations, sometimes there is only one intersection point. In the case of inequalities, when we talk about a set of solutions, there's going to be a set of ordered pairs or an infinite amount of set of ordered pairs that could potentially satisfy any sort of inequality. Now, when we graph these inequalities, because we're going to want to draw these things out based on any sort of inequality they give us, we're going to sketch it out very roughly on the Cartesian plane, and then we're going to sketch in the region or shade in the region in which the points technically could exist. Now, a couple things to consider in that process. When we're graphing inequalities of two variables, you must consider, are we going to draw a solid line or a broken line for the boundary? And then do we shade above or below the line? So let's take a look at the following example. First and foremost, when you graph these things, you always want to have them isolated in terms of the y variable or the output, because we always say that our y is on our vertical axis, our x is our horizontal, where x is the input, y is the output. All right. One thing you're going to notice about this is that this is actually a y equals mx plus b type of situation. We have a linear line, which is the whole focus of this lesson. I'm just going to write this off to the side here. We have y, which is equal to mx plus b. This is a symbolic of this, which means our slope in our situation is equal to 1, and our b value is equal to 2, which is the y-intercept. So now what we're going to do is we're going to plot this out. Starting off with a y-intercept of 2, I'm going to put a point there, and then a slope of 1, well, that's 1 over 1. And then we go up 1 over 1. And so we're going to get a couple more points that look like this. We could even continue that pattern, and it would look like this. We could continue the pattern below by going down 1 to the left by 1, and it would give us the following points that make up the boundary line. Now, what we want to do is we want to sketch through this, but it's important to distinguish, are we going to use a solid line or a dotted line? And the way we can tell is if it's included, meaning it's less than or equal to, that means that it is a shaded boundary line. We do not have a dotted broken boundary line. It's a solid line, and we say solid because it's included. As soon as they say less than or equal to, or that inequality includes the equal to, we're going to have that. I want you to put arrows on the end representing that this boundary line will extend left and right to infinity unless it has certain bounds. And now we want to talk about it having a shading above the line or below the line. Well, to consider where this boundary line, if it's solid or broken, first and foremost, let's just answer that question. It is solid. And in brackets, I'm just going to put y. It is the less than or equal to that made it solid. Do we shade above or below? Well, because it's all the y values that are less than this line, what we're going to do is we're going to shade everywhere below. How I'm going to do that is I'm going to maybe just use color like this. What you can do is you can actually just take your pencil and just do a light shade in this region like this. There we go. So there's our solution region. Anywhere here could be a potential solution. And then from here, do we shade above or below? We shaded below. Notice the boundary line that divides it into a 2-half plane. When we look at this here, we should notice that we have two regions. One region above the line or above the boundary, a second region below the boundary. Now, let's use a test point to check and see if this green region actually is the appropriate region for this. So what I'm going to do is I'm going to put a dot maybe right here. So if I put a dot here, the ordered pair that actually goes with this is -1 and 1. And so let's use this to see if this actually works for us. Okay, first and foremost, we go y is less than or equal to x plus 2. We're going to plug in our y value, which is 1 is less than or equal to, and I'm just going to make that less than or equal to above just a little bit neater. There we go. So that's going to be less than or equal to, our x value was -1 and then plus 2. So now we get this as our solution, that 1 is less than or equal to -1 plus 2 is 1. Hey, look, it works. There you go. Perfect. We know that this region, in fact, works. And we could do this for as many points as possibly needed. And what I'm going to do is just backtrack this a little bit. I'm just going to arrow over off to the side here. So we'll say that 1 is less than or equal to -1 plus 2 is 1, and therefore this works. We have verified that the left-hand side would equal the right-hand side, or the left-hand side is less than the right-hand side. Okay, perfect. Now, we can choose any point we singularly want in there. It doesn't matter which point we choose in there. Any of the points would satisfy this, including even if we chose one right on the boundary line, it would work because the boundary is included. So therefore, we would get something that would be equal in this case, or something that would allow it to be satisfied into this inequality. Okay, let's take a look at a second example. We're going to go through all the same steps, including shading and potentially using some points. Graph the inequality. In order to graph it, we must isolate for y. So let's write this again. This is going to be 2x plus 4y, not 2y. There we go, is greater than 8. I'm going to start by subtracting the 2x across because I see I have a positive amount of y's on the left-hand side. This becomes 4y is greater than -2x plus 8. Our last step is to divide by 4 because we don't want the 4 attached to these terms here, or to the y value, I should say. And now what this is going to give us is that y is strictly greater than 2 over 4. Well, this is -1/2 x. And then the 8 over 4, this gives us positive 2. Now, just a couple characteristics to pull. We have our slope, which is 1 over 2, -1 over 2, that is. And then we have our b value, or our y-intercept, which is 2. Awesome. Okay, we know it's strictly greater than this. First of all, we got to draw our boundary line. In this case, let's start by plotting out some points. So we know our y-intercept is 2 because it's the b value. And now we need a negative slope. We go down 1 over 2, down 1 over 2, down 1 over 2, and we get a line that looks like this. We go in the other way, left by 2, up 1, left by 2, up 1, and we would get this line here. Now what we're going to do is we're just going to sketch a line through this to represent that it is the boundary line. And I'm going to hope that it goes through neatly. If not, we can always freehand this, but I would love if it does this. Perfect. We're going to put our arrows on the end representing that it goes left and right. Unless they apply specific bounds to this, we're going to put arrows on the end because they didn't restrict the domain in this situation. They didn't say it could only be a certain amount of x's, or they didn't even restrict the range in this situation. So if the range and the domain aren't restricted, just write out left and right to infinity. Now what we're going to do is we're going to talk about all the checklists with this one here. We've graphed the inequality. Here it is, but part of graphing the inequality is also shading the region or sketching the appropriate region for this. When we did our inequality and we isolated it for y, we found that the y values must be greater than and strictly greater than this. So what we need to do is we need to adjust our boundary line in the following way. And I apologize for this if you need to erase. We need to make this a dotted line. We need to make this a dotted line because we know that the boundary line is not included. If the y value is strictly greater than 0, as we see here, and I shouldn't even say greater than 0, but if it's greater than this piece here, as soon as you see greater than or even less than, we need to make sure that we put this as a dotted line or a hashed line like this, because if it's solid, that means that it's included. Okay, now we're going to go through the checklist of this piece here. So we want to say that if the y values are all greater, then our region that we're going to shade is up here. There it is. So we're going to include all of this stuff here. We don't want to include the boundary line. So I almost should go back just a tad and just not make it go overlapping on the boundary line, because if it overlaps the boundary, that might be bad for us because it definitely is not included. So as you can see, I'm being very careful not to shade the boundary on this situation. And I love how I did that on the last one. There we go. Perfect. That will be as good as we can get it here. Awesome. And then now what we want to do is we just want to pick any point in here to verify that it works. So if we know that y is greater than or it's above the boundary line, then I'm going to choose some point. Let's say I choose 1 and 4 up here. So I'm going to plug in 1 and 4 to the inequality and see if it satisfies it. To do this, we're just going to test it and go, well, I know 4 is greater than negative 1/2 times 1 plus 2. Okay, this is 4 is greater than negative 1/2 times 1 is just negative 1/2. Negative 1/2 plus 2, this gives us positive 1 over 2, or 3 over 2, I should say. And 3 over 2 is going to give us this piece here, which is, in this case, yes, less than 4. Because 4, if I converted 3 over 2 to a decimal, it'd be 1.5. And so for this situation, 4 is definitely greater, and therefore this satisfies it. And we could even choose another point if we really wanted to. Why don't we choose something like negative 2 and 4? Or actually, that might be boring because we're using the same y value. Maybe we use something like this one over here. So this is at 1, 2, 3, 4, 5 in terms of y. And then in terms of x, it is at 1, 2, 3 and negative. So we're going to write this as negative 3 and 5 as the point. Let's just see if it satisfies this. So 5 is greater than, or the y value is greater than, negative 1/2 times the negative 3 plus 2. 5 is greater than, well, this is negative 1/2 times negative 3, which is positive 3 over 2, plus 2. And then if we added these things together, we would end up getting where 5 is greater than 3 over 2 plus 2. This is the same as saying 3 over 2 plus 4 over 2, which is 7 over 2. And 7 over 2 we know is 3.5. So yes, 5 is definitely greater than 3.5, and it works. Perfect. So any any point we chose from that region in green, all of those would satisfy this given setup or satisfy this given inequality. If I chose a point down below, what I would find is that, let's say I chose this point, if I went to substitute it into the inequality, it would end up breaking the inequality and making it so that it was not an actual solution because it wouldn't satisfy the inequality. Okay, again, let's just generally review the rules for the boundary line. If the inequality is a strict greater than or less than, then we know it's going to be a broken boundary line, or a dotted boundary line as we call it. If it's greater than or equal to or less than or equal to, we call this a solid boundary line. And then after isolating y in the inequality, then we can either shade above or below, because we'll say, hey, if we know that y is greater than a certain value, then it's above. If it's less than, then it's below. And that's why we say after isolating y, then shade. And then simply saying for this one, if we know that it's greater than, we're going to shade above. And so maybe we just highlight that piece here, because I think this is an extremely important note here. After isolating for y, then we shade above or below depending on the direction of the inequality. Now, the easiest test point to use is 0, 0. However, you can use any point that you would like. 0, 0 is the easiest one to use because often, if you look at it, 0, 0 is right here. This is outside of the boundary, so this would immediately go against it. But if we're trying to prove that it actually, there is a certain point, then we couldn't choose 0, 0 for this one, because 0, 0 would lie outside of this and it wouldn't actually satisfy it. So this would almost be like a test point that would just be a counterexample for this situation. You always want to choose one within the defined region. Okay, now let's go on to example 3 here. Two positive real numbers, m and n, are related by the inequality 4m minus 3n is greater than or equal to 24. What are the restrictions on m and n? Well, they actually just listed them. They're right here. Two positive real numbers. That was right off the hop of the problem. So what we're going to do is we're going to define these as m must be greater than or equal to 0, meaning it must be a positive real number. And then once it's past 0, m can be any real number. Or not any real number, but in this case, I guess, yeah, because it's a positive number, any real number that's positive, that seems fair. For our n values, same thing. We want our n to be greater than or equal to 0 because it must be positive real numbers. And then once it's greater than 0, it can be any real number in the positive real plane. There we go. Okay, now when they say graph this inequality, what we're going to need to do is, first and foremost, I'm going to set the n values to be my y-axis. I'm going to set the m values to be my x-axis. And I mean, you could reverse these if you wanted. It won't really matter. You'll get the same solution. But for this situation, I'm going to make my n's my y's, and I'm going to make my m's my x's. Now, if that's the case, we need to take this original inequality and isolate it for n. So I'm going to start by doing that. I'm going to write out the original, which is 4m minus 3n is greater than or equal to 24. Awesome. And then I'm just going to make that a little bit better for us. Perfect. Now, in order to isolate this, I'm going to first of all move the 4m because I don't like that a 4m is attached to my left-hand side. This is going to give us negative 3n is greater than or equal to negative 4m and then plus 24. Now, here's that trick that we're going to see again from our first part, or 9.0. When I divide by a negative attached to the variable, when you divide by a negative across the inequality, you're going to see that the sign flips. This will be n is now less than or equal to 4 over 3 will become positive because of the double negative. So 4 over 3m, and then 24 over negative 3 is negative 8. There's our new inequality here. Okay, now from here, what we want to do is we want to write out our slope. And just to avoid confusion here, instead of calling it the m value, because typically we call it the m, I'm going to call the slope, because I don't want to mix it up with the m within the problem. Our slope is 4 over 3. And then our y-intercept, which I'm going to use as y-int, is negative 8. Now, here's an unfortunate piece about this specific situation, is that when we look at this, our y-intercept is, based on this graph, is not even visible. It's way, way down here. If we were to go to negative 8, it's actually somewhere way down here. So what we're going to do is we're going to solve for the x-intercept of this one, or what we're going to call the m-intercept, and that's by setting the n value equal to 0, which is technically our y in this situation. So let's just do that algebra off to the side here. If I want to get the m-intercept, this is 0 is equal to, and then I'm going to make this the 4 over 3, which is the slope, m minus 8. 8 will go to the other side, making this 4 over 3. Perfect, 4 over 3m. I'm going to multiply both sides by 3 in order to get it from the denominator there. Now this is going to give me over here, I'm going to get 24 is equal to 4m. And then lastly, I'm just going to divide by 4, divide by 4. And when you divide both sides by 4, we get an m-intercept equal to 6. So this means that the point for our m-intercept is going to be 6 and 0. And now that we have an m-intercept, what we can do is we can plot that. So we're going to go 1, 2, 3, 4, 5, 6 over. That puts us right to here. Perfect. And then if this is our m-intercept, now we can use our slope to plot out a bunch of the other points. So what I'm going to do is I'm going to go up by 4 units. So 1, 2, 3, 4, over by 3, and that puts me here. I'm going to go up by 4 again, 1, 2, 3, and 4, and over 3. So that would put us up 4, 1, 2, 3, right here. There we go. Now we can draw the line, but we just need to be very careful. Is it going to be a dotted line or a solid line? We go back to our inequality, and it's a less than or equal to, meaning it is a solid line because the boundary is included. So I'm going to go back to here and then draw a line through it that is solid, connecting all those points. Hopefully, there we go. Excellent. Arrows on the end because there was no restriction on the domain and range. And then again, we just want to make sure, where are we going to shade? Well, because it's all the n values that are less than the line, when it's less than or equal to the line, it means it must be below. And so what I'm going to do is I'm going to shade everywhere that is below. And it's okay if I shade the border in this case because it's included, whereas the last problem, I didn't want to shade the border because it was a broken line, and broken lines are not included. Okay, there we go. So there's our borderline. There's the solution region, which is below the line because of the less than or equal to. And now they say write 3 ordered pairs that are in the form of m and n in terms of an x and y that satisfy the inequality. Okay, for this one, we're going to just pick 3 points in this given region and then discuss them and label them. So let's say I choose right here. So this is a point is 1, 2, 3, 4, 5, 6, 7, 8 for x and 1 for y. I could choose another point like this one here. This one is going to be 1, if I guess that's 8, that's 9 and 10, and then up, so this would be 10 and 4. And then because the boundary is actually included, I can use one of those boundary points. So let's say that I want to choose this point up here, which is on the top right. This one is going to be at, well, if that point's 10, then it's 11, 12, and then up 4 points from that, it is going to be at 12 and 8. Perfect. So these are 3 points we could use. Now, realistically, you can choose any points, including points that are down here. You could choose points here. You could choose points here. You could choose any point on the line. there's an infinite amount of points you could select. So we're going to write these below and just say, for example, or i.e., we had, for our first point, it was at 8 and 1. We then had another point, which I just want to make sure I get right, at 10 and 4. And then we had another point at 12 and 8. There you go. Okay, now again, these are just examples of points. They're not all the points, but they're just some examples that satisfy this inequality. Just to make sure that they satisfy the inequality, you could always go back and then just plug these into the inequality. So if you were skeptical of any of these points, take them, plug them back in here, and be like, if the n value is this, then if I plug in the m value, will it be that the n value is less than or equal to the m? And for any of these points, it should work. All right, lastly, we're going to go on to this situation where they say, let's write inequalities to describe the following graphs. So this situation relies on us kind of working backwards in a way, because in the first case, we were given the equation, or the inequality, I should say. And when we were given the inequality, we could sort out what was the y-intercept, what was the slope, which allowed us to sketch out some points. We had the inequality in terms of, is it greater than or equal to, less than or equal to? We had all that information, so it was easy to sketch. Now in these situations, we're working backwards. So first and foremost, we need to figure out what is the y-intercept. Y-intercept is right here. So we have a y-intercept at 0 and -2, and this is our b value, so that's why it's so important. We also need to figure out the slope. We need to go between 2 points that we know. So I'm going to go from here and go down and then over. So we go from 2 to -2, which means we decrease by 4 units. We go from -2 to 0, which means we go over by 2 units. Therefore, the slope is going to be equal to, and yeah, let's just do it off to the side here. The slope is equal to -4 over 2, which is the rise over the run. Therefore, the slope is equal to -2. Now that we have a slope and a b value, what we're going to do is say, therefore, we now have y. And then here's where the inequality comes in, because we got to be very specific with this. If we know that the shading is above the line, we clearly see that it's all above. If I was to sketch this out all the way to infinity in the left and right, above the line is considered to be up here. And then if this is above the line, it means that our inequality, first and foremost, is that it is greater than or equal to. Now we put our slope together. It's -2x plus whatever our y-intercept was. But in this case, because it was -2, it's going to be -2 like this. So there is the inequality that represents this graph. Perfect. Okay. And then again, I'm just going to annotate right below here that we put this piece here, the greater than or equal to, because it is a solid line. There we go. Okay, now let's go on to the second graph. Very similar, another linear line. So we need to establish two critical pieces. First and foremost, we need to figure out what is the y-intercept. The y-intercept is 0 and 1, which is symbolic of our b value. We then need to figure out the slope. We just need to go between any two known points. So we could go here to here. And if we go up or we rise by a certain amount and we go over, we're rising from -3 to 1, which means we go up by 4 units, and we go to the right by 2 units. Therefore, if we calculate our slope, it's going to be slope is equal to the rise over the run. Therefore, my slope is equal to +2. And it should make sense that for this one, it is positive because we're increasing as we're going left to right. Now what we want to do is put these things together. Therefore, the equation is y. And now we want to determine this again. Is it above or below the line? In this situation, it is above the line again, because if I extend this out to left and right, then above the line is considered to be up here in this shaded region here. Now, that means that we're going to put greater than or equal to start this problem. We then put our slope, which is 2, connected to our x, and then our y-intercept was +1. And then again, I'm just going to underline this and say it is because, so we have a, oh, and whoa, I need to make sure I get this in the notes. I'm catching it as I'm working on this here. If we realize that this was a solid line, right? That's why we put the greater than or equal to. Because this is a dotted line, it's not included, and therefore this should be strictly greater than. There we go. Now this is better. We put this because we know it was a broken line. Yeah, wouldn't want to put equals to, because if you see that broken line, you know that it's not included, And so if I said that it was included, then that's going to be causing issues. So look for that on the graph. And then again, think about these things as we're working backwards. You're building out an equation of a linear line. Linear lines always have the equation of y equals mx plus b. So you need two things, a slope and a y-intercept. And then if you can get those two things, it comes together quite quickly. The only like really difficult or new logical decision you need to make is, hey, is it greater than or equal to, less than or equal to, meaning a solid line, or is it greater than or equal to, or greater than or less than, meaning it's a broken line where it doesn't include the boundary. All right, this is where you're going to want to get your practice. So good luck with the practice. Move on to the textbook, try out as many as you can, and then we will potentially have a show on this. All right, good luck.